In this example, we'll be looking at the catalysis to get from the hydrate to an aldehyde. So here's the aldehyde. And a water molecule is the side product here. We don't need any other reactants. This is an elimination reaction. And our catalysis options are acid or base. So, under the acid conditions, let's use HCl in this example as our strong acid. One of the hydroxyl groups can be protonated. That prepares it to act as a good leaving group. So it can be pushed out by the lone pair of the adjacent neutral oxygen. That forms a carbon-oxygen pi bond with a plus charge on the oxygen that donated its electrons, and it kicks out a water molecule that's neutral. The conjugate base of the strong acid that we used is one option for what base could be used for this last step. The water could also do this, but we'd have some extra steps to prove that the acid was catalytic in terms of balancing, so this is the simplest option. We've regenerated the original catalyst that we had. And so mapping our products here, here's the water molecule that is a stoichiometric product. And here's the acid catalyst. Let's just mark that with a different color. Here's the acid catalyst that got regenerated. If we run this reaction in the reverse direction, we'll start from the aldehyde. The strong acid can protonate the aldehyde carbonyl. A water molecule, as the stoichiometric reactant, can attack the carbonyl. So here's the oxygen that just attacked. It has a positive charge. And the conjugate base of the strong acid that we used can act as a base. Which regenerates our strong acid. So let's map this. We have a strong acid that was used catalytically and then regenerated. And we have a water molecule that was stoichiometric, that was used as a one equivalent reactant. We can do the same reaction under base conditions. So let's switch to another color. Here's our base conditions. Hydroxide, as the example base here, is going to start by deprotonating one of the hydroxyl groups on the hydrate. that negative charge is now a strong reactive site in the molecule, which can kick out a poor leaving group, hydroxide. That forms the aldehyde functional group directly and a new hydroxide ion. So if we're mapping this and we think about a catalytic amount of base being used, here's where we regenerated that catalyst at the end. And if we're looking at where's our stoichiometric product, we haven't actually drawn it in, but we did generate it with our curved arrows because the water molecule that was made at this stage doesn't get used again. It's the stoichiometric product here. In the reverse direction, we can start from the aldehyde. And now that I've plugged my computer in so I don't run out of battery, here's our aldehyde. Thinking about a reaction with hydroxide ion present. Here's the hydroxide. It's going to go ahead and directly act as a nucleophile in the first step. Here's the hydroxyl group that used to be the hydroxide ion. We have a water molecule that is going to act as a stoichiometric reactant, and here's the protonation that we need to explain. This provides the hydrate product and a new hydroxide ion as the conjugate base of the weak acid that we just used. So if we're mapping this reaction, we can see we used a hydroxide ion over here and we regenerated one over there. So we've explained using a catalytic amount, and we have used one equivalent of water overall during the reaction. So here we are zoomed back out to the big picture.